But today is good afternoon, everybody. Great pleasure to have here Andrei. It's a great pleasure to have here today. It's excellent research with a lot of achievements from he's also a very good friend in Paris, a great supporter of activities in Region 9 of IEEE, so Latin America. So Andrei received the master and PhD degrees in the University of California, Berkeley, where he was a key contributor to the famous SPICE simulator. So he pioneered the electrical simulation parallel computers with the CASS simulator as part of his PhD. And he's the author of the SPICE book, published by John Willing and Sons. For many years, Andrei was director of research and development, leading the design and implementation of innovative software and hardware electronic design automation products for companies such as Analog Devices, Valid Logic, and Cadence. Currently, he's a professor at the University of California at Berkeley and at the Institut Supérieur d'Électronique de Paris, France, involved in research projects with other major universities. His research activities are in the areas of design, simulation, and modeling of semiconductor devices and ICs, applications of new devices and circuits for quantum computing. Andrei is also a IEEE Life Fellow and a CASS Board of Governors member. So thank you very much again, Andrei, to accept our invitation. And now I give the floor to you. So now you have the control to start your screen sharing.
Thank you very much, Ricardo, for the invitation and also for this very nice introduction. So I'll take over the screen now. Let's see, I'll bring up my presentation. So is my presentation visible?
Yes, now you just have to put in a presentation mode. Okay, perfect.
So you give me the go ahead.
Go ahead.
All right, thank you.
Thank you.
In my presentation entitled CMOS for Quantum Computing, Devices, Circuits, Modeling, and Simulation, I'm going to describe the key role that CMOS technology has today in the race for building a quantum processor capable of solving problems intractable for today's computers. This work is taking place at the QTech laboratory at the Technical University of Delft under a grant from Intel Corporation. First, I will introduce briefly what is a quantum computer and describe its system architecture. Then I will ask the question and give an answer, of course, whether MOSFETs can work at helium temperatures where a quantum computer needs to operate, followed by the design issues of the quantum and electronics interface, and describe a simulator called SPINE developed for this purpose. And finally, I will address some of the procedures to design these interface circuits and give some examples of present implementations. So this person asked, what is a quantum computer? Can we build a quantum computer? And he had some outrageous ideas. Proposing to use entanglement and superposition, quantum mechanical concepts, for a future possible computer. Even himself was wondering how feasible these concepts would be by entitling his book, Surely You're Joking, Mr. Feynman. This was a bestseller for many months on the New York books list. So The concept was there in the 80s, but it was a concept that came and went. Only until recently that research in quantum computing took off connected with the level of technology development that we have today. Now, if somebody asks what is a quantum computer, it's probably described as the application of quantum mechanical phenomena, the ones that we mentioned from Feynman, superposition and entanglement, to perform much faster computation and solving problems like encryption, decryption, DNA analysis, molecule and drug synthesis, and so on and so forth. The unit of information in a quantum computer is called the quantum bit or qubit. Unlike its current equivalent, the bit, which has two states, 0 or 1, the qubit can be in a multitude of states in between a 0 and a 1. It is implemented as either the spin of a particle called spin qubits, such as an electron qubits, or the state of Josephson junction resonator, and then this would be the superconducting qubits. The state of the qubit, represented by psi in this equation here, as you can see, it has a certain probability of being in the state 0 or the state 1, and all its possible positions can be represented on what is called the Bloch sphere, shown here. Now, where does the power of the quantum computer stem from? It's the fact that if I have only one qubit, I can have two states. If I have two qubits, I will have 4 states. 3 qubits, 8 states. And so I go on an exponential increase of memory and computation power, such that if I would have 50 qubits, which is doable today, it's close to the state of the art, that would represent 2 to the power of 50 complex amplitudes, and this would represent a memory larger than a memory of the largest supercomputer today. All these basics are presented by Lieven van der Sijpen in a keynote that probably you can find also on YouTube at the International Solid State Circuit Conference in 2017. So the other part, so we've seen what superposition is. The other thing is entanglement, which is defined as 2 particles are entangled if the quantum state of one particle cannot be described independently from the quantum state of the other particle, or in practical terms, measuring the quantum state of one particle implies knowledge of the quantum state of the other. Now, let's have a look at what is the solid state quantum bit implementation today. So first we have the semiconductor quantum dots, where one can isolate a single electron and control its spin in an energy well. Then we have the superconducting circuits, where I can represent a qubit as the state of one of these resonators. And then there is an in-between solution, a hybrid solution between the two. In our work, we have focused mainly on the semiconductor quantum dots. The state-of-the-art implementations today, you can see qubits integrated on different chips, like 72 qubits for Google, 16 qubits for IBM, which is an online version where people have access, 49 qubits for Intel, and Rigetti also with a 19 qubit chip. Now, the architecture of a quantum computer is shown schematically here. So, on one hand, we have the quantum processor containing all these qubits, and these qubits, in order to be able to be coherent, or in order to be able to control and read their state, they need to operate at temperatures much lower than 1 degree Kelvin, typically at 20 millikelvin. On the right-hand side, we have the electronics, what we call here the classical controller. In order to perform operations on the quantum bits, we have to generate a number of signals in order to position the qubit in a certain state. This representing a quantum operation, or the qubit at the same time. It's not only the unit of information, but it is also the elementary quantum gate. So once these signals compared to corresponding to operations performed by the computer, they are applied, then the resulting state of the quantum bits needs to be read and interpreted by, again, electronic circuit. So the two roles that the electronic controller has is the manipulation and control of qubits and implementing operations and reading out the final state. Now you have here a schematic view of a quantum computer today, where the quantum processor is in a dilutional refrigerator at 20 millikelvin. There are a number of, another connectors, and so in the refrigerator, and all the electronics you can see is outside. So this poses a problem, because you realize we must have a lot of connections, cables that go between one and the other. So a practical view now of how things work today is shown here, where let's say the quantum processor is here at the bottom at 20 millikelvin, and probably we can have up to 50 kilobits, because this is how it's done today. And the controller, the electronics controller, is somewhere in another room where you have all this instrumentation. And between the two, we have all these cables that go between 20 millikelvin and room temperature. And you can realize from these pictures that, you know, it won't take too much, more than over 50 or maybe maximum 100 of these cables that can go from through the refrigerator before filling up its whole volume. So the concerns are, well, this is bulky, it's expensive, it's power hungry, obviously limited wiring, and of course, very important is the cooling power. How much cooling power can we afford? And how many useful bits do we have today? Well, you can see that we are limited here only to a bunch of around 50 to going to probably towards 100. But really, to solve the problems that you know, we herald that the code that the quantum computer is going to solve, we need you know, for molecules and encryption and so on, to have an exponential increase, something like a Moore's law, to achieve these levels, and maybe we'll need like hundreds of thousands or millions of qubits. Now, you are asking, why a million qubits? Well, the problem is that you need a lot of redundancy in qubits. You know, if you have maybe 1,000 qubits, maybe only you're using 100 of them, as so you have physical qubits and logic qubits, and the one you use for computation are the logic qubits, and you need all this redundancy for error correction and so on, because of issues of noise and correctly interpreting the state of the qubits. So can we think of a better solution? And now, given that the quantum devices operate at these millikelvin temperatures, how about cryoelectronics? And this, so here are our qubits, and we get rid of all this instrumentation here at room temperature, but we bring the electronics close to the qubits. And this idea, I think, was first put forward by my colleague and friend Eduardo Charbon, who, were talking about this in 2014 when nobody believed in it. And then he had a presentation at IEDM in 2016. Now, bringing the electronics close has many advantages. Of course, we take advantage of the scaling of CMOS, which translates into scaling of quantum computer capabilities, a number of qubits, high speed integration, and so on. But there is, okay, so the concept of the scalable quantum computer is, okay, all the electronics now we move, let's say, at liquid helium, like at 4 Kelvin. And then we'll have tens of thousands, hundreds of thousands of channels, which can obviously achieve only using VLSI CMOS. But the question comes up now, fine, cryo-CMOS, great idea, but does it work? So the question that we need to answer is, how do MOSFETs behave at liquid helium temperature? So in order to give the answer to this question, we built a number of test chips in two technologies, in 160 nanometers and 40 nanometer CMOS, both thin oxide and thick oxide transistors. And here you have the measurements shown for the two types of the thin oxide and thick oxide. These are all for 160 nanometers. And the first thing we notice is that the current at 4K solid lines is considerably higher than the one at 300K. And this is explained by rough doubling of the mobility at a very low temperature. Now, a counter factor is that the threshold voltage also increases, but a small increase of the voltage of the threshold does not offset the gain from mobility. Another very positive factor that logic designers would love is that the subthreshold slope is increased. I mean, the slope itself is higher by a factor of 4, but so the number of the slope is smaller. So instead of like let's say 100, would have like 25 at this temperature. However, we have also unpleasant surprises. Look at this characteristic for the thick oxide transistor here. You can see something that maybe reminds you of the partially depleted SOI, where we have this kink coming up in the ID versus VDS characteristic. Now, obviously, this is a no-no for analog designs, and actually we need very accurate analog circuits to drive and interpret the results of a quantum computer. So this would be really a showstopper. Now, why is this happening? At cryogenic temperature, there is an effect known as freeze out. So the substrate is really getting its resistance very high up to the hundreds of megohms or higher, where when we have carriers that go to the substrate, they will raise the potential inside the substrate, leading to, at some point, a slight forward biasing of the source substrate junction. And this leads to a sudden decrease of threshold voltage, explaining the jump in current. Okay, so how about the 40 nanometer CMOS transistors? Now, all of a sudden, pretty much we observe the same effects with higher current due to mobility, a little higher threshold, same kind of improvement in subthreshold slope. But the good news is that there is no kink effect. We look both at thin oxide, at thick oxide, they are perfectly behaved. Well, there are many explanations for this, starting with the higher doping as well as the lower voltages that we apply for 40 nanometers. So first idea here is that 40 nanometers, 20 nanometers, and so on technologies should work perfectly to implement it, to implement this cryogenic CMOS circuits. Now, in order to design these circuits, obviously we need models. We need to simulate and verify the designs that, as you'll see a little bit later, have to satisfy very stringent constraints. Now, the test chips that we we had from the foundry MOS 11 or PSP models. Now, it's known that these models, they're physics-based, they solve the surface potential. So we found that it is not that hard to match parameters for extending the validity range of these models down to cryogenic temperature. Of course, there are physical effects like a substrate freeze out that are not present in the models. So the models needed to be upgraded in order to be able to match these nasty kinks that we get in the older processes like 160 nanometers, and particularly in the thick oxide transistors. But even here, as you can see here, we did a great job managing to upgrade the models in order to represent this region as well. Now, the challenging part remained right at the transition between strong inversion and weak inversion, the moderate inversion region, as you can see here. But even here, the discrepancy is not that high. Now, for 40 nanometers, things are much more straightforward because we don't notice the substrate freeze out. Matching is perfect, even going from strong inversion to subthreshold. And we took the challenge and see if all these transistors even work down to the millikelvin range where the qubits operate. And sure enough, from going from the same characteristic was shown at 4K, going to 1K, we see very good operation, expected operation, both for NMOS and PMOS, and even at 100 millikelvin. So all these results are presented in Journal of EDS paper on characterization and compact modeling nanometer CMOS transistors. And here in this slide, actually, we represent the subthreshold slope going down to millikelvin regimes. And we can see here that at some point there intervenes a saturation that below 1 Kelvin, we really don't get a bigger advantage, but that's perfect enough. As you could see also in the previous characteristic, we get almost a vertical straight line in subthreshold. Now, additionally, this same type of conclusions were shown also for fully depleted SOI and FinFETs at 22 or lower feature sizes. And one reference here is from Beckers from EPFL on these other technologies. Now, another thing that we need to worry about is variability and mismatch. Again, because we need to design and implement very accurate circuits. So we start with the variability model of Pelgrom, defining the standard deviation as a function of the size of the transistor. And there is an associated mismatch model that known as the Kroon model, which uses the Pelgrom standard deviations to give estimation of the variability of the drain current. In order to characterize this device, we built a test chip with 33 identical pairs and measure to characterize the standard deviation for VT, beta, and ID. Obviously, even close to each other, the two transistors will not have the same current, as you can see here. So we did a number of tests on 33 pairs measurement, from which we could derive the standard deviation shown here, at which obviously increases at lower overdrive voltage. Then we performed mismatch sweeps as a function of VG for different temperature from 300K to 4K. The dotted lines are measurements. The full lines are the prediction of the Kroon model. And as we keep laying them one over the other, we can see that there is almost a saturation going to low temperature below, let's say, 150K. There is no much more deterioration in mismatch. However, the difference between room temperature and lower temperature is pretty high. Obviously, the mismatch worsens. The Kroon model fits very well. An important observation here is that as the gate overdrive voltage reduces and we're hit at the same time with an increase of threshold voltage, the mismatch takes off at these low voltages and low temperatures. Now, how well does the Pelgrom model hold? We have characterized here three different aspect ratio geometries and drawn the line that would match these points according to Pelgrom's model. And from this, what first of all we can realize that they match well. Of course, the standard deviation increases both for beta and VT. But also the very interesting factor is how does this technology-dependent constant A that shows up in Pelgrom's equation evolve with temperature. We can see that for the threshold voltage, there is not much change, maybe 20%. But for beta, we can notice a 2x increase, which then obviously explains the much worse matching that we have at cryogenic temperatures. Okay, so with this, let's go now and talk about the quantum electronics interface. Now, the challenges are very high in designing this interface because, as I mentioned, in the very high level system view of a quantum processor, we need, first of all, we need the electronics to generate the signals that these are high frequency RF signals that control the movement and the state of the qubit. Now, we need to be very accurate in these signals because otherwise the error in positioning as a qubit in the state that we want may be prone to error, which obviously will involve even a higher error by reading back. So we characterize the accuracy of our operations by the fidelity of an operation, which ideally would like this fidelity to go to 10 parts per million. Of course, you know, this is an ideal wish. We may actually have to compromise somehow between the different characteristics, performance characteristics like the frequency, the amplitude, the duration. You know, each of them will have some acceptable error, but overall we need to match a certain fidelity, even if it's not 10 parts per million, it's 100 parts per million or so. We need to see where can we have some negotiation in order to improve one specific parameter. And that parameter that we're after, especially because we have limited refrigeration power, is circuit power. Try to reduce as much as we can circuit power. Now, for this reason, we built emulator, simulator, how you want to call it. It's SPINE, standing for a spin emulator, which solves the synchronous behavior between electronics and quantum system. There would be no other way to be able to predict correctly that our circuit will satisfy the fidelity in the different parameters performance that we expect. So first of all, how do we solve the state of the electron? Now, for solving psi, the qubit state, we need to solve Schrödinger's equation, which is represented here. And as you can see, it's an ordinary differential equation where H is the Hamiltonian, which describes mostly the electronic system. You have here the signal, the microwave signal that we impose, that we control the qubit with. Now, obviously, there are quantum simulators that will solve this equation. And the first thing these solvers do, they change a time-dependent, they transform the time-dependent Schrödinger equation in a time-independent quasi-static solution where we partition the time interval in discrete time steps, and we search a solution, a unitary operation U, which represented the operation, let's say, at time I, n plus 1, and so on. And the solution of the state would be the product of all the different instances of the U vector imposed on the initial state of psi to give us the solution at the time. Now, if we look at this schematic and all this operation of solving the time solution of psi, we notice that the same algorithm is used in SPICE. SPICE does the same thing in solving the ordinary differential equation of a circuit. So why not syncing the two in the time domain and solving them at simultaneously at the same time step? Now, the way we introduce the quantum solver to work with SPICE, we developed Verilog A models where the Verilog A model actually instantiates the quantum solver. So this would be a 2 qubit system where we apply as input the RF signal to the qubits, and we solve at each time step for the U operator as in terms of magnitude of phase, U being a complex quantity. Now, obviously, Verilog A is portable. It's supported by all the simulators. The implementation we've done is in Cadence, such that we can have the entire simulation in the Virtuoso framework. And here to the right, a little more complex, is if we have two entangled qubits that need to be solved. The design methodology is shown here, where we define first the requirements of the quantum processor. We get signal specifications as shown before, and we use SPINE for this. We define the control architectures of the circuits that we're going to use, and then we use SPICE to simulate repeatedly the quantum specification with the circuit designs, and we go back to our system level verification and we optimize circuits or we change initial conditions. As an example, we take here an output driver of the RF signal, a simple output driver that we need to design in order to achieve a certain power minimization. So we can somehow negotiate on the gain accuracy. As we can see, around 20 gigahertz where we have our signal, the transfer characteristic of the driver is pretty constant. We have a wide margin of bandwidth here. So we may reduce a little bit the high requirement on the amplitude of the amplitude accuracy, therefore reducing the bias current and therefore minimizing the power. And in order to find the sweet spot, what will be happy to accept as fidelity, let's say we accept a fidelity of 99.9%, we can, using spine, trace all the different characteristic points of the qubit fidelity for different performances of the gain, values of the gain, and see that if we accept this 0.1% fidelity, the sweet spot would be right here, what gives us the relative amplitude from which we can design the whole circuit. So the electric noise has a limited effect, and therefore we reduce the total power consumption. Now, to go and see the usefulness of this methodology and of the spine emulator, we take as an example a system level verification where we have the control electronics represented by a behavior model of the controller providing the length of the operation of the control signal, like for a pi operation, pi over 2 rotation, and so on. So this is represented at a very log A level. Then the role of this circuit is to provide the signals in order to achieve a sequence of rotations that I will explain and visualize later on the qubits, and define the resulting signals. Now, besides the signal controlling the operation, we have the RF signal that controls the rotation, the spin of the electron. Now, the mixer is a very crucial element, so we model it at the transistor level, and it will generate the signals applied to the qubit, and the response of the qubit is represented by the Verilog A model in spine, where everything then can be simulated together, and the operation and the response of the qubit can be seen. So overall, we have analyzed the spin emulation, mixed signal simulation, and RF simulation, so all together within the same virtuoso framework. Now, how does this operate? So in this animation, we're going to see when we start applying a signal, first, the electron just spins and spins until the RF signal is sent. So the signal here is along the y-axis, right? And the electron spins around the x-axis. So in the xy plane, so for a 50 nanosecond of signal, we achieve no, I think this will be 25 nanoseconds. We achieve a pi/2 rotation, and then if the signal is collinear with the spin of the electron Rx, we see no change, and then we obtain another pi rotation. Okay, so this illustrates how the signals generated by the electronics actually control the operations and the evolution of the state of the quantum bit. Now, this other slides, they just show in bits and pieces the progression. Actually, we can do them, we still have time. So this would be the pi rotation, followed by pi/2 rotation, and followed by yet another pi/2 rotation to bring back the qubit in its initial state. More information on the whole electronics can be found in the ISSCC 2020 paper of Patra and Van Dyck and others. So, okay, we have hopefully convinced you of the usefulness of CMOS in building a quantum computer. Now, where is the proof? Well, the proof consists in 2 generations of chips of control electronic cryogenic CMOS chips that we have developed, starting with the first announcement in a solid-state circuit conference in 2017, where here you can see the LNA of the readout circuit, and here you can see the actual RF signal generator. So the different arrows shows how the different components come in the overall schematic. Now, the current generation, the next generation, so these first chips were built in 40 nanometer CMOS. The current generation that was announced at ISSCC this year, they have the code name Horse Ridge, designed and implemented with the help of Intel in 22 nanometer FinFET. And again, you have the same components, the signal generation, but now this represents much more complex chips being able to control higher number of channels of simultaneous quantum bits, like you've seen that we have 49 qubits, and the new chips can control all these operations. Now, the detailed description of the Horse Ridge chipset is already available on early publication of the Journal of Solid-State Circuits, and makes the point and proof of the viability and usefulness of CMOS for quantum computing. So, in conclusion, we show the vision of quantum processor controlled by CMOS, where the CMOS ICs are placed close to the quantum processor at operating at liquid helium temperatures, and probably in the future we're going to be able to bring them even to lower temperature. Obviously, power is constrained here of how much power we can afford. Now, we've proven that CMOS operates normally down to millikelvin, And in order to be able to design the circuits that we had in mind, we built simulation models to support the IC design, and we have verified these models by measurements to be accurate within a few percentage points. Now, to complete the design, the challenge was the interface, quantum electronics interface, for which purpose we developed the spine emulator, enabling the co-simulation, synchronous co-simulation of the quantum part and the electronics part. We've implemented the co-design methodology during development of the different chips, allowing not only exhaustive verification of the quantum computer, but also the negotiation of specs of how we can find the sweet spot of the best characteristics and the minimum power. And last but not least, 2 generations of cryo-CMOS control ICs were fabricated and demonstrated and published. I will leave you with this view of a future quantum computer, which obviously has many different levels, and there are people worldwide that work on each of these levels, on each of these layers. And a quantum chip with millions of qubits is envisionable in the future, and obviously we'll need to also in parallel develop the verification and methods tools in order to achieve this grand project. Last but not least, also I would like to acknowledge, as I mentioned, the grant from Intel Corporation, and the achievements presented would not have been possible without the great contribution of our QTech students, Jeroen van Dijk, Pascal Hart, Rosario Incandela, Bishnu Patra, and Gerd Kine. Thank you.
Thank you very much, Andrei. It was a very nice talk in a hot topic. So I have already here some questions. First one from François Rivet from Bordeaux. So bonjour, Andrei. Thanks for your nice talk.
Bonjour, François.
Do you think it will be physically feasible to reach a sufficient level of integration control of physics to get a quantum computer at home in the future? For instance, in my living room or in my pocket? Can we imagine to cool down a chip at 20 millikelvin outside of a lab? My cellar is not cold enough.
Well, Francois, for the foreseeable future, I think we'd better work on the ones in your cellar, because I don't think that it's for our next 10, 20 years that will make the quantum computer work at a 1 cellar temperature. So for right now, I think we still depend on the big refrigerator.
So next talk by Professor Palomino, how the external magnetic field can affect the spin position?
Well, you mean the interference of an external magnetic field to the one that we try to impose?
I suppose so.
I think that with the proper shielding, I don't think that we should have any issue with this.
So another question by François Rivet again. Do you think quantum computers should be taught at master level during electrical engineering studies? Do we need to train future quantum engineers?
Yes, I think so, and especially because electronics, as we see, is intimately related. I mean, you won't have a quantum computer unless you have the electronics to control and interpret the results. So I think it's a perfect fit of, especially thinking that in France, students study for 2 years quantum mechanics. They have some basics already of quantum mechanics. This is just extending the electronics curriculum and bringing back some of the concepts they learned, obviously not at the same level as a physicist to teach it, but for the application purpose of being involved in the design, operation, because most of the people will actually use a quantum computer. But, as when I was talking about SPICE, I would say, well, in order to be a good and knowledgeable user of the simulator, you need to understand how it works, because otherwise, if you accept blindly what the simulator is telling you, you may be on the wrong track. So the same thing is, I think, with a quantum computer, where understanding the way it operates is important. And even if some of the students are not going to design a quantum computer, they will more effectively know how to use use in the sense of programming a quantum computer, because it's not like the assembler of the classic computer. The operations are completely different, and if you just stay at the user of the algorithm level, then maybe you are shielded. But if you are a programmer of a quantum computer, you need to understand how it works.
So we have a question by Walter Calienes Bartra that you
Hi,
do
Walter,
well.
how are you?
So his question is, how reliable is a quantum computer in radiation environments?
I should have expected this question, because we worked on CMOS under radiation, right? Well, again, I think that the quantum processor itself, in the current and near future environment of the dilution refrigerator, is shielded pretty much from radiation. So on the spot now, I don't see an issue.
So a question by Michael Sieberer. When you were still using bulk CMOS, did you look at the STI corner parasitic devices? What do you observe? What did you observe?
I'm not sure. We didn't look inside the structure, actually. What happens, we just did the electrical characterization, not going in detail into the device structure itself.
Question by Denis Flores. Hello, Andrei. Thank you for your presentation. Can a quantum computer compute directly from continuous values from analog sensors, such as voltage, current, temperature, and audio?
Well,
audio, sorry, to finish the question, audio and video, or is an intermediate conversion to a discrete or digital value needed?
Well, as you can see, the representation of information is continuous by superposition or the superposition of all the states that a qubit can be in. So I would not need digitization, because the signals, so the code, right? I have a quantum code. it is translated into analog signals that are used to actually perform the operations on the qubits. So I think that everything, if I understand your question right, can be done at an analog level. It's just how your voltages and currents are transmitted in the sense of operations to be imposed, to be controlled, to control the qubits.
The question by Juan Pablo Brito from CETEC. So, can you see in the future end user personal devices like smartphones or notebook with quantum processors inside?
No, absolutely not. It's like the concept of the cloud, right? I mean, your individual device, your terminal, can only do certain parts. You know, if you want to do scientific things or, yeah, I don't know, decrypt something on your phone, then you'd have to access somewhere in some place a quantum processor, because again, maybe I didn't stress enough that the quantum so-called computer is not an independent computer like today's standard computers, but it is more like an attached processor where you prepare the problem that you send to be solved by the quantum processor, and then you get the results back. So a quantum processor would always need a front end that sets up the problem and then retrieves the answers.
The second question by Juan Pablo also. The 3-4 semiconductors have an advantage of other semiconductors over standard silicon for cryoelectronics?
The honest answer is I don't know, but I don't really see what advantage they would have, especially that we're talking about CMOS characteristics that are, at least today, not reproducible, like the high scalability, high integration, low power, and so on, that we can have in CMOS today. So for right now, I would say I don't see any advantage.
Okay. A question by Clovis Fickenbaum. Seems to me that the temperature is one of the biggest issues concerning quantum chips. For that reason, wouldn't it be better used for space station or long-time missions on outer space, since on that environments the temperature is always much lower than here on the ground? And I can add that much lower than the cave of the cellar of Francois.
Now, if I understand your question correctly, you'd rather place the quantum processor in space?
I think he's asking this, yes.
Well, you know, it's a futuristic, very futuristic idea. Maybe Elon Musk would get excited by this.
Okay, question by Matthias Batarsi. You talk about the qubit being also the fundamental gate. I didn't get it in what sense. Could you expand on that?
Okay, well, let's look at an inverter, right? A classic inverter, I present a signal at its input and it gives me a 0 or a 1, okay? Same situation with the qubit. I present a signal, as I showed you, to its input, and its state is going to move from state X to state Y. So the rotation that the state vector of the qubit performs represents an operation in a quantum computer.
So now a question by Michel Castriota. How the flicker noise of transistors changes at 4K? Thanks for the nice presentation.
Well, if I'm trying, well, the flicker noise, I mean, all the noise, not only the thermal noise, but all noise should flicker noise included, should be reduced due to the fewer interactions with the interface should be reduced.
Okay, another question by Dennis Flores. How much power, energy, does a quantum computer require for a given task? How expensive is a quantum computer for a given task, especially compared to the cost of traditional digital computing?
Well, obviously, in a quantum computer, we're limited by how much power we can cool. What is the power requirement in order to keep the 20 millikelvin? So, you know, I'm not, I don't have exact number on the refrigeration technology today, but obviously the cost of operations is much lower in a quantum computer. Already we had figured out that if we build, you know, if we build the electronics next to the chip that has the quantum bits, we can not afford more than like 1 milliwatt per qubit. So you know, the budget of the whole circuitry that we add should not, you know, be more. Should be in the one watt or maybe to 10 watts. That, but not more than that.
So a question by Mahesh Chaubey. Interesting topic, nice talk. Professor, I have question about which process is good for designing the cryogenic circuit?
Well, as I mentioned in my talk, proof has been given that all the current processes, I mean CMOS, so we have experimented with bulk CMOS from 40 nanometers. We have shown that if you go to older processes like 0.16 micron, it's not that good. That you know, we may have kinks in the characteristics, which again are not desirable in analog circuits. So any technology, bulk CMOS technology below 40 nanometers should be fine. Fully depleted SOI, it's again a very good technology for building these circuits, and also FinFET, as proven by the Horse Ridge chipset in 22 nanometer FDSOI. No, sorry, FinFET, 20 nanometer FinFET.
Okay, so I think we have no more questions. There was already a nice set of questions. So thank you very much again, Professor Andrei, for this excellent talk. And we had today, I think, around till 90 participants. And we had participants from USA, France, Chile, Germany, Italy, Colombia, Ecuador, and many locations in Brazil. So thank you very much again for your very nice talk. And,
thank you again, Ricardo. Thank you, Ricardo, for inviting me. It's always been a pleasure to to respond to invitations from Latin America, and I hope that your public in Brazil and other South American countries have enjoyed the talk. Thank you.